So my name is Energy Infrastructures and Geotechnologies, what a long name, in Bochum, Germany, at the Competence Center for Post-Mining Exploitation. And I wrote my PhD thesis about stratification in flooded underground mines. So I would like to talk about this topic and then also find a direction to geothermal applications. So first of all, just this general question, when we do investigations or when you carry out investigations in flooded underground mines, there are few factors or few aspects we have to consider. So first of all, we have to look at the mine layout. We need to see, is it a single or multiple shaft mine? We need to look at the history and especially also at the post-mining phase. So is the mine still in the flooding process or is it already flooded? We need, of course, to look at geology and also consider hydrogeology or hydrogeological investigations. I have this little picture here. Excuse my drawing skills. But you see that mine water samples for hydrogeological investigations can be taken at different locations in and around the mine. And now you have to ask yourself, when you investigate a flooded underground mine, are you taking mine water samples only at the point of discharge or at the top of the flooded mine water body or inside the mine water body as well? Because I will show you in a second, this will lead to different results. So why different results? Because in most of the flooded underground mines, we have density stratification, and sampling results then can look like this. So see on the left side, if you take a mine water sample, just on the top of the flooded mine water body, you get certain values. And if you assume this is the entire mine water body and you assume, okay, I can use these values, these results for my conclusions, and this is the mine water body. But usually that is not the case because we find stratification in flooded underground mines, and this is the right picture. So on the top, you have different water quality on the top, and at the outflow, you have different water quality than inside the flooded mine. So shortly, a few facts about the research history when it comes to stratification. Stratification in flooded underground mines, and now I'm always talking about density stratification, was first studied in the 1960s in the US. Stewart and Simpson wrote the presence of layering in acid water. So this was the first time when stratification was described in scientific literature. And in the subsequent years, investigation was done by sampling in the flooded shafts. So usually now we use, for example, this sampler. This is from the German company Sea and Sun, and with this one that we used in my former research group, we can investigate temperature, electrical conductivity, and pH value. And of course, the pressure, and what we usually get are temperature profiles. So, and electrical conductivity profiles. So you can see these two profiles here over depth. One, the temperature, and on the right side, the electrical conductivity. And you can also see there is a distinct stratification. So in the upper water body, we have a temperature of 19 degrees Celsius and around 800 microsiemens per centimeter, which is quite a not so high electrical conductivity, almost groundwater value. But then in the lower part of the mine, below level 200, we have a temperature of about 23 degrees Celsius, so 4 Kelvin difference, and also an electrical conductivity of over 4,000 microsiemens per centimeter. So you can see here very, very clear stratification. And with these temperature and electrical conductivity recordings, it's possible, for example, with the UNESCO equation, to calculate also the density stratification. Since the 1990s, there are different modeling approaches. For example, Jessica talked a little bit about it. And in the more recent years, the focus was also on the barrier function of stratification. That means that there is not really an exchange between the different water bodies. And in the last years, and this was also the topic of my PhD thesis, we looked more at a comprehensive studies to compare different mine sites and the different water bodies with each other to be able to make general statements about stratification. So I have an example here for you. Remember in the last slide, I showed you the temperature and the electrical conductivity profiles. And these profiles were from this former uranium mine in Portugal. See, very kind of complex multiple shaft mine. We measured in the Puco Santa Barbara shaft, in the main shaft, and the point of discharge is at shaft P4. And what we have here is a warm mineralized water body. And in the last years in the stratification research, we tried to implement this term because it's coming from ocean science, but we think it really fits and we need some terms that are used from all of us to make it not more complicated, because in the last years people use different terms for the stratified water bodies. So we would like to implement warm mineralized water body and cold fresh water body, the CF and the WM water bodies that you can see here very clearly in this mine. And just to show you how important the stratification is in this case, so I said at shaft P4, we have the point of discharge. And because the water quality, remember, it was just around 800 microsiemens per centimeter, is relatively good. At a former uranium mine, we can have a passive mine water treatment system because we have this barrier function of the stratification and the really nasty bad mine water stays deep down inside the mine. So what are the further investigation approaches? The comprehensive assessment of over 60 mines, available temperature and electrical conductivity profiles, and available cross-sections for the mine, because it's really important to see the mine layout, what also Thomas just explained, and compare it with the temperature or electrical conductivity profiles, and to find cross-links between the mines. This is how it looked, just a few examples. So multiple shaft mines, single shaft mines, different commodities. I had ore mines, I had coal mines, really to get a general impression. And then I made a database with subsets of the water bodies, and I had different criteria how to analyze this database. So for example, the depth of the intermediate layer. The intermediate layer is that layer that that is between the warm mineralized and the cold freshwater body. I had a look of the mean and the median temperature of the cold freshwater body of the warm mineralized water body, at the depth profile itself, and also at the depth of the mine shaft and many other parameters. So what are the results of the comprehensive assessment? So first of all, in really almost every flooded underground mine, there is stratification. And in most cases, the cold freshwater body is above the warm mineralized water body. There's no correlation between the mine type, so let's say single shaft mine, multiple shaft mine, and the stratification or the number of water bodies. And usually we have 2 or 3 water bodies. You see this in the diagram on the right side. So 1 water body means no stratification, 2 water bodies means 1 warm mineralized water body deeper down and 1 cold fresh water body. Or if we have 3 or more, we have 1 cold fresh water body and then several warm mineralized water bodies. There are really large ranges of the minimum and maximum water temperatures or electrical conductivity. So for example, in the cold freshwater body, we had temperatures between 5.3 degrees Celsius and 32 degrees Celsius, and really large jumps as well. So this difference between the upper and the lower water body. So for example, there were jumps that were only 0.1 millisiemens per centimeter, but also jumps that were 163 millisiemens per centimeter. And here I have another profile for you from a former coal mine in Germany with really, really high temperatures. So the upper water body already has a temperature of 30 degrees Celsius, and the lower water body even has a temperature of about 42, 43 degrees Celsius. Furthermore, it's important that the location of the stratification is usually at the topmost intermediate layer. so between the cold freshwater and the warm mineralized water body, and it's usually in the upper part of the mine. So at the first or at the second connected level to the shaft, like you can see it here at this former coal mine in Germany. But there are also a few cases where we have no stratification. These are really just a few cases, and we basically can also explain in every single case why there was no stratification. So in some cases, we think that the galleries might have broken down and there was no hydraulic connection anymore, but we can't prove this because we can't go down with the camera there or check it in any other way. But we know that in some other cases, and this were the main cases, that there was a disturbance of the stratified water bodies due to forced flow, in most cases due to pumping activities. So what else did we figure out from our observations? That the warm mineralized water body or the boundary between the cold freshwater and the warm mineralized water body is mainly determined by infiltration water, and that there are different hydrodynamic processes that influence the occurrence and the location of stratification. And I think this is a picture that you have to have a look when you have some time. So I just left a QR code for the publication here, and you can have a look. But you can see there are many different processes that really influence the occurrence and also the location where the stratification occurs. All right, a few more slides. First one, to show you that there are really different stratification scenarios. So the first one is if we have natural discharge. There can be either no stratification, but it's really seldom, stratification at the first level, or stratification at some lower levels for whatever reasons. For example, in the mine map, there is a top level, you can see a top level, but it's sealed or it's broken down. So then the stratification is deeper down in the mine. Then different scenarios is if you have pumping activities. So, and these are just some thoughts. We can prove this in some cases, but not always. But we think that if you have a low pumping rate and you pump above the stratification, it's less likely that the stratification will break down. If you have a high pumping rate and you pump above the stratification, it's more likely that the stratification will break down. If you have the pump close to the stratification, the breakdown is really likely. Next case we leave out for now. And then if you dewater the mine, of course, the stratification will break down.
Okay,
And now,
5 minutes.
finally, all right, finally, we come to geothermal exploitation without lowering the water level. And these are just some thoughts, some hypotheses, because we need to experimentally prove if these ideas are correct. So just to share with you our ideas, that if the pump rate equals the withdrawal rate and you have a sufficient distance from the pump and the stratification, it's really less likely that the stratification breaks down. But if the pump rate equals the withdrawal rate, but you pump inside the warm mineralized water body, so below the stratification, it's more likely that the stratification will break down. And within a closed loop system, the stratification breakdown is less likely. And as I said, it needs to be experimentally proven, which Professor Wolkerstorfer in South Africa is doing right now. He has an analog model of a flooded underground mine, which is 6 by 4 meters large. And in this analog model, we can play around with these different scenarios and figure out more which influence pumping, for example, for geothermal exploitation could have. So last slide. Pumping activities, well, forced flow might break down stratification, and this can lead to worse water quality. If pumping is necessary, for example, for maintaining the water level or for geothermal applications, you should really investigate if there is stratification in the mine water body. It's advisable to keep the pump rate low and to keep distance to the intermediate layer to the stratification. Also important, don't switch the pumps on and off, because this changes the mine water pH, and this leads again and again and again to chemical reactions and to the change of the water quality. And you should really consider that the water quality could become worse. And this needs to be included in the entire mine water management, because at the beginning you might pump water with much better quality, but if the stratification breaks down, the water quality could get worse, and you need to consider this in the entire process. So at the end, more research about stratification and geothermal applications are needed, because we know now quite a little bit about stratification itself, but not so much in the context of geothermal applications. And yeah, that's my presentation. And if you have any questions, you're welcome, or you can also send me an email. Thank you so much.